Alright, well this screencast is going to help you all with acceleration as well as something called the equations of motion and their use. Well, if you start off by asking somebody what they think of when they hear the word acceleration, they'll probably say something like a car speeding up, or it means gaining speed. Some people might say, or it could mean slowing down too. That might be a negative acceleration or a deceleration. But typically people think acceleration is simply speeding up or maybe slowing down. Well, a really good scientific definition of acceleration is the rate of change of velocity. It's the rate of change of velocity. And you may say, well, I told you so, it's speeding up. Well, remember, velocity is related to speed, but it has direction. And so, for instance, if you were to take an object, a ball or whatever, and if you were to tie it to a string and spin it in a circle like this at a nice steady speed, it turns out that that ball on the string has a nice steady speed. It's not changing its speed, but it happens to be accelerating. And the reason it's accelerating is because it's changing its direction. Here it was traveling to the right, here it was, or east, let's say. Here it's traveling north, and then west, and then south. And as it's changing its direction, it's changing its velocity. And anytime something changes its velocity, it's accelerating. So here's a case where an object is not speeding up nor slowing down, and yet it's accelerating. So we want to remember that acceleration is the rate of change of velocity. And if I were to write that in an equation form, here's what it would look like. It would look just like this. A equals delta v divided by t. Now first of all, this t comes from the word rate. Anytime you use the word rate, you're saying a quantity is divided by time. So for instance, speed is the rate at which distance is covered. Distance, rate, gives you average speed, right? Well, if we talk about the rate of change of velocity, rate means we're going to divide by time. And what are we going to divide by time? We're going to divide the change in velocity. And remember, that triangle there means change. It's that Greek letter delta. And we've got our v representing velocity. And this is going to equal acceleration. Now we could also write this equation like this. A equals v minus v naught. When you hear me say the word naught, it's what scientists use to represent that, or to speak of that little zero down there. And that means initial velocity. This over here is a final velocity. And if you take the final minus the initial, why, you have the delta velocity, or the change in velocity. So really these two equations, this one over here and this one, they're saying the same thing. And then what you're doing is you're dividing by the time interval. And this is how you calculate acceleration. It's the change in velocity divided by time, or it's the rate of change of velocity. Now the car I happen to be driving right now is a Nissan Altima, and if I hit the gas or put the pedal to the metal, I bet I can go from 0 to 60 in 4 seconds. I don't know if that's true or not. Maybe I'll try it on my way home. But given those numbers, an interesting question would be, what is my acceleration over that time interval? Well, to figure that out, you're just going to go ahead and do acceleration is the change in velocity divided by time. Change velocity is final velocity minus initial velocity, or v minus v naught, divided by the time interval. In this case, my final velocity would be 60. My initial velocity was 0. And this is miles per hour. And then I'm going to divide by 4 seconds. And so when you get a calculator out and you use 60 divided by 4, you get 15. And the big question now is, what are the units? You know, the units for speed our miles is miles per hour, or meters per second, or millimeters per year, or furlongs per fortnight, or something like that. It's any distance divided by time. But here, when we're talking about acceleration, we have some units that look like this: miles per hour per second. And those are really strange units. You can see that there's one type of distance there, and there's a couple times, but these are units for acceleration. So at this point, we probably want to ask, what does it mean to be accelerating at 15 miles per hour per second? Well, the key here is really thinking about what these units mean. These are units of speed, 15 miles per hour, and these are units of time, seconds. And what we're saying is we're going to gain 15 miles per hour of speed every second. Or another way to look at it is I'm going to change my velocity by a positive 15 miles per hour every second. So, at the end of 1 second, my Nissan Altima is going to be going 15. At the end of 2 seconds, my Nissan Altima is going to be going 30. At the end of 3 seconds, it's going to be going 45. And by the time I hit the 4th second, I'm going to be at a whopping 60 miles per hour. And we're going to say, boy, did that thing accelerate. Now, let's say I'm traveling 60 miles per hour, and I slam on the brakes, and I come to rest, or I stop after 2 seconds. What's going on there? Am I accelerating? You bet I am. I'm changing my velocity. Let's see what type of numbers we can work with. My initial velocity in this case was 60 miles per hour. I'm kind of just driving along, minding my own business, and all of a sudden a deer comes in the road, and I hit the brakes, or maybe I hit the deer, and regardless, my speed drops to 0 miles per hour. So I went from 60 down to 0, and let's say this happened in a time interval of 2 seconds. In this case, what is my acceleration? So what we do is we get out the equation. A is change in velocity divided by time interval. Change in velocity in this case is v minus v naught, or final minus initial speed, or I should say final minus initial velocity. And my final is 0, my initial is 60 miles per hour. And I'm divided by a time interval of 2 seconds. And when you do that, you're going to get negative 30 miles per hour per second. And so at this point, it would be right to say that when I hit the brakes, I accelerated at a rate of negative 30 miles per hour. Oops, I left off something there. Per second. And what does that mean? Well, it means that over that 2 second time interval, my speed, or my velocity, is changing by an amount of negative 30 miles per hour each second. And that's what it means to accelerate at negative 30 miles per hour per second. Now, some people like to use the term decelerate for that event. I don't typically like to use that term, although it's accurate and true here. But it just turns out that there are times you're going to find out that negative accelerations can actually mean you're speeding up. If you think, well, what's he talking about? Well, let me tell you. Let's say your car is headed to the right at 30 meters per second. That's somewhere around, those are different units instead of miles per hour, but we're talking somewhere over 60 miles an hour. But anyways, 30 meters per second, you're moving to the right. And if that's your initial velocity there, let's say, for instance, you were accelerating at a rate of positive 5 meters per second per second. Well, if you're going to accelerate at a rate of positive 5 meters per second, that means you're going to gain 5 meters per second of speed every second. So at the end of 1 second, you're going to be traveling 35. At the end of 2 seconds, you're going to be traveling 40. At the end of 3 seconds, you're going to be traveling 45, and so on. But what if now your acceleration was actually negative 5 meters per second per second? Well, at the end of 1 second, you're going to be going 25. At the end of 2 seconds, you're going to be going 20. At the end of 3 seconds, you're going to be going 15 meters per second. So you're saying no big deal. That's what I thought. A negative acceleration means you're slowing down. You're decelerating. Oh yeah? Well, check this out. What if your car is traveling to the left? Now its velocity is no longer 30 meters per second. Its velocity is negative 30 meters per second. And what if you have a negative acceleration? Well, turns out that when your velocity and your acceleration have the same signs, it always means speeding up. So in this case, if you're traveling to the left at negative 30 meters per second, and if your acceleration is to the left at negative 5 meters per second, turns out you're going to be speeding up to 35, and then 40, and then 45, and so on. Wow, I didn't know that negative accelerations can make you speed up. Sure, if you're headed in the negative direction, which we are right there. Well then, could positive accelerations make you slow down? You bet. Let's say my car is headed to the left at negative 30 meters per second, but my acceleration is 5 meters per second, or positive 5 meters per second, or 5 meters per second to the right. Well, now what it means is my car is going to slow down from negative 30 to negative 25, and then to negative 20, and then to negative 15. And so what you always have to watch are the signs on your velocity and your acceleration. If the signs are different, then there's going to be slowing down happening. If the signs are the same, either both positive or both negative, then there's going to be speeding up going on. So keep that in mind when you're dealing with accelerations. Now when we talk about acceleration, it's the right time to start talking about what are called the equations of motion. The equations of motion are some complex equations. They're equations that are more difficult to use than just v equals d over t or a equals delta v over t. There are just more variables involved. And these equations come from either a study of calculus, or they can be derived from some graphical methods used in a laboratory. In this screencast, I'm just going to give you the equations of motion, tell you what the variables represent, and how they can be used to predict future events involving velocities, times, and displacements. And here you have it, the 3 equations of motion. Let's take a look at this first one right here. This one is actually quite familiar, because if you consider just the definition of acceleration, you would recall that a equals change in velocity divided by time. But we can write change in velocity like this. And from here you can see that, wow, if I were just to multiply both sides of this equation by t, and then if I were to add the v naught to both sides, I would just have this same equation right here. So this first equation of motion is really just based on the definition of acceleration, just rearranged algebraically. And you want to be sure you know that, of course, a is acceleration, t represents time interval, v naught represents initial speed or initial velocity, and v represents final velocity, or the velocity after a certain amount of time t has passed. In the second equation, a of course is acceleration, t is time. Notice how the time in this equation is squared right there. And there's a time also right in the first part of that, and then there's the initial velocity or initial speed, and then we have displacement or distance. Now you hear me talking a lot about displacement, distance, speed, velocity. I'm kind of using these terms interchangeably. And you know what? It's fine. You can use them interchangeably as long as you're headed in the same direction the whole time. In other words, if I'm always headed to the right, then it turns out that this displacement can also equal distance. However, if I'm moving to the right and then over that same time interval I start moving back to the left, Now this